now examine the regions of operation for the transistor, and we'll start with the cutoff region, and we'll look specifically at the NPN. The operation for a PNP is very similar, with the majority charge carrier being a hole rather than an electron. So in the cutoff region, we know first of all that no current flows. Alright, so let's look at a cross-section of the device and figure out exactly what's happening. So in the cutoff region, we know that we set a voltage across the base to emitter junction to be less than 0 volts. And we similarly set the base to collector junction to have a voltage of less than 0 volts. This is our emitter, the base, and the collector. And of course we have N plus, P minus, and N minus in these regions. Now effectively we have PN junctions, so we form parasitic diodes at these junctions, and these diodes are both off. Now when the diodes are off, what we have are depletion regions. In other words, charge carriers, or electrons, in the N minus region are drawn towards charge carriers in the P plus region, and they bind together to form pairs at the surface of this junction, or what we would call a depletion region. Because the carriers are all bound to one another, they don't want to move, and hence we have effectively an open circuit, no current flowing. The same thing occurs at the PN junction between the base and the collector. The electron hole pairs are bound to one another and don't want to move, and so we get a depletion region there as well. Now one would note that the area of the amount of concentration of the carrier has to do with how thick the depletion region is. So the N plus region, which has more carriers, would be thinner than the P minus region, which has fewer carriers, and hence would need a wider region to have the same amount of charge to bind to every particle in the N plus region. So we can say, in general, with these devices that the emitter is doped heavier than the base, which is doped heavier than the collector, or our concentrations would go something like N plus is greater than P minus is greater than N minus. But we have an open circuit here, at least in terms of a DC circuit, so our symbol could basically be replaced with an open circuit. Or if we were looking at AC analysis, these depletion regions would look kind of like capacitors, so we could put capacitors between the base and collector and base and emitter. This capacitor is typically called C mu, and this capacitor is typically called C pi. So the base to emitter capacitor is called C pi, and the base to collector capacitor is called C mu. Now we won't examine the other regions of operation other than the forward active region, because we don't use reverse active or saturation very much. So next we'll look at forward active region. Okay, in the forward active region, the base emitter junction is forward biased, so the diode's on. The base collector junction is reverse biased, so the diode is off. So if we look at the cross-section of our devices again, we have our emitter, N plus, base, P minus, collector, N minus, and here we put a voltage across the base emitter junction where the base to emitter potential is greater than 0. And we put a voltage across our base to collector junction such that the base to collector voltage is less than 0. In other words, the collector voltage is higher than the base voltage. Now, what happens here is first, electrons are injected from the base to the emitter, or sorry, from the emitter to the base, exactly the opposite of what I intended. So we have these E- electrons that are sent into the base. Now ideally, these go straight through the base and into the collector. But because there are some holes in the base, some electrons recombine with holes in the base. So some of these electrons are going to fall out and go towards the base, making a base current. Finally, we have holes injected from the base to the emitter. So we have H plus going back into the emitter. These constitute a forward collector current, or a current going from the collector through to the emitter, called IC. Again, we have negative charged particles flowing in this direction, and corresponds to a positive current flowing in the direction from collector to emitter. Now we'd like to minimize that base current, so we'd like to minimize the number of, we'd like to minimize the base current. And so what we want to do is minimize the amount of recombination that occurs in the base and the number of holes, the injection of holes into the emitter to minimize the base current. And so to do this, we want to do two things. Well, we can't do it as circuit designers, but perhaps we could advise device designers to do this. We want a very thin base material. So the way I've drawn it, I've drawn the base to be very thick, but in reality we'd like the base material to be very thin. Now this makes sense because if we have a thin base material, then as the electrons move through the base, there's less time for them to recombine with holes. And secondly, we want the emitter to be heavily doped, more heavily than the base. And this makes sense also because this means that we'll have fewer holes for electrons to recombine with. All right. This being the case, we've tried to minimize the base current. We can define a forward active current gain in the transistor called beta forward, and this is defined as IC over IB. Now we also know that our collector current, IC, is just given by a diode current, which is equal to some saturation current, I sub S, times E to the V BE over V capital T, our thermal voltage. The thermal voltage is, of course, 26 millivolts at room temperature. So for beta forward, we'd like to have a large collector current and not a very large base current, or a very small base current, which means we want beta forward to be large. Sometimes we define a second parameter called alpha forward, which is just equal to beta f divided by 1 plus beta f. And you can see that if beta f is large, this is approximately equal to 1. Now, one thing that we've mentioned is that the collector is not the same as the emitter. Even though they're doped with similar particles, we dope the emitter much heavier than the collector. And what this means is that beta reverse, which would be the reverse current gain, is much, much smaller than beta f. And this would mean that if we were to derive a similar alpha reverse, that it would be much less than 1. Now, in the next part of the lesson, we will look at biasing the transistor to be in the forward active region and then extracting what we call a small signal model so that we can figure out what the AC gain is for these devices.